So we left off chapter 16 here, so this is part 2. The cyclopentadienyl cation, in terms of Huckel's rule, it predicts that the cyclopentadienyl cation with 4 pi electrons is anti-aromatic. So with this prediction, the cyclopentadienyl cation is not easily formed. So you can't take the cyclopentadienyl and react it with acid so that it leaves. This does not occur. So in terms of cyclopentadienyl ions, the resonance forms. Over here is a cyclopentadienyl anion, which has 6 pi electrons and it's aromatic. Below is the cyclopentadienyl cation, which has 4 pi electrons and it's anti-aromatic. While it does have resonance forms, it's not necessarily stable. So if we look at the electrons, showing how the electrons are moving, here this moves around in this form. Again, it moves. And those are all the possibilities. In terms of the cation, electrons are now moving from the source, the double bond source, as such. There you go. Cycloheptatrienol cations is 6 electrons, and with an empty p orbital, the cycloheptatrienol cation is easily formed by treating the alcohol with dilute aqueous sulfuric acid, as shown here, and in which case what happens is the electrons from the oxygen pick off the proton, and then once it picks off the proton, you have, so I'm going to actually draw the OH over here, since I have room. Sorry, it's a substituent coming out. Here's your other H. So this is positively charged. As a result, the electrons will go to the oxygen, leaving as water, generating your tropylium ion, that's what it's called. And the other representation shown here when it's in resonance is showing the circle inside. In terms of cycloheptatrienol ions, the tropylium ion has 6 pi electrons, is aromatic as shown above. The anion has 8 pi electrons and it's anti-aromatic if it's planar. Again, the resonance picture here gives a misleading suggestion of stability. Just in terms of movement of electrons follows as such. And for the anion, again, the source of electrons is going to be your double bond, not double bond, in this case your 2 electrons. And as such, there you go. Cyclooctatetraene dianion reacts with potassium metal, shown here, to form an aromatic dianion, shown here. The dianion has 10 pi electrons. As a result, you can represent that as a circle inside with 2 minus charge. And as a result, 10 pi electrons is aromatic. So if we were to assess whether a compound is aromatic, here this is non-aromatic, non-aromatic because there's an sp3 carbon in the ring, so the delocalization would not be complete. This would be aromatic, right? There's 6 electrons, 4n plus 2, obeys Huckel's rule. And all the carbons are sp2. Sorry, I crossed that out. Pyridine. So pyridine is like benzene, except with one of the carbons replaced with a nitrogen. And so this has 6 delocalized electrons in the pi system, and you have a lone pair electron that is not part of that pi electron system. Pyridine is basic and has a pair of non-bonding electrons that can react and abstract a proton. So in this case, you have water, and it'll abstract in the presence of water ions, or the hydrogen from water, generating the protonated pyridine, or the pyridinium ion, shown here, and it's still aromatic. Again, because the pi electron system is still there. In terms of pyrroles have a nitrogen shown here, and these electrons are actually, the non-bonded electrons do participate in the pi systems, yielding 6 pi electrons. And yes, and because it has 6 pi electrons, it obeys Huckel's rule, 4n plus 2. As a result, it's aromatic. Pyrrole in the presence of water. Here's your sp2 nitrogen. pK is 13.6, so it's a weak base. In the presence of water, those electrons will pluck off the hydrogen from water, leading to the N-protonated pyrrole on the right side, as you can see here. And so, again, the electrons in that P system are being delocalized. When it's protonated, right, you no longer have that electron, those electrons here, so then it becomes 4, and it's now non-aromatic. Basic or non-basic, pyrimidines have 2 basic nitrogens over here. Imidazole has 1 basic nitrogen over here, and then in pyridine only 1 of these nitrogens are not basic, which is this one. So all of these are basic, which means that these electrons are not part of the pi system that leads to their aromaticity. So an important thing to note is that most non-basic or pyrrole-like nitrogens have 3 single bonds and a lone pair p orbital, while most basic or pyridine-like nitrogens have a double bond in the ring and their lone pair in an sp2 hybrid orbital. Other heterocycles, so we talked about cyclopentadienyl anion, pyrroles. So furan is when you're substituting your nitrogen now with an oxygen, or a nitrogen, a carbon with a sulfur substitution, leads to thiophene. In these cases, the electrons, right, you have 2 lone pairs for both the thiophene and the furan. One of them does participate in the pi electron system, while the other one is available for a reaction. So is the molecule below aromatic, anti-aromatic, or non-aromatic? So in here you have 3 nitrogens. These are 2 nitrogens from the pi system. This nitrogen lone pair actually participates in the p orbital for that pi system, while these 2 are available and basic. So as a result, this gives you 6 electrons, and the 6 electrons make it aromatic. Polynuclear aromatic hydrocarbons, here are examples of them. So they're essentially fused benzene, in different fusion states. So this is anthracene, this is phenanthrene, and you can show it as such, or because they are aromatic, you can show them in these forms as well. In terms of naphthalene, naphthalene is the 2 fused ring system, and it's the simplest fused aromatic hydrocarbon, and it's shown here. And here are the different resonance forms that you can make. In the first case, you can have electrons move as such, yielding this compound, and then you can have electrons move again as such, yielding this compound on the right. Larger polynuclear aromatic hydrocarbons are shown here: pyrene, benzopyrene, dibenzopyrene. These are formed in combustion. An example of that would be tobacco smoke, and many are carcinogenic. So they form epoxides, and as a result, when they form epoxides, they react with DNA base. So, example, here is benzopyrene. In the presence of oxygen and just enzymes, liver enzymes, you will form epoxide over here at the 4,5 position, or here at the 7,8 position. These are arene oxides. The arene oxides will then react with the DNA base. Here's an example of cytidine. We'll do nucleophilic attack, open the ring, and now form what is called an adduct to the actual DNA. And then when transcription and translation occurs on the DNA, you're going to have this adduct, which will affect that process. Allotropes of carbon, there are 3. One is amorphous, the next is diamond, and the other one's graphite. Amorphous, they're in small particles of graphite, charcoal, soot, coal, carbon black. Diamond has a lattice tetrahedral carbon of atoms, as shown here. And then graphite has layers of fused aromatic ring. This would be a single layer of graphite. And a single layer of graphite would also is graphene. Diamond. It's essentially one giant molecule that is highly organized. It has a tetrahedral of carbons. Sigma bonds are about 1.54 angstrom, and they can serve as electrical insulators. Graphite. Graphite are planar layered structures shown here. The layer fused benzene rings have a size of 1.415 angstroms. Only van der Waals forces exist between layers, and they can conduct electrical current parallel to these layers. There are new allotropes, fullerenes, and nanotubes. So fullerenes are shown here. They're 5 or 6 membered rings arranged in a soccer ball structure. And then nanotubes, they're half of that C60 soccer ball structure fused to a cylinder of aromatic rings. There are examples of fused heterocyclic compounds here in amino acids. In proteins, L-tryptophan shown here is a fused heterocyclic compound. Here's benzodarone, which is a vasodilator, and again it's showing a fused cyclic compound. LSD is also a fused cyclic compound, and the quinine, which is an anti-malarial drug, is a fused cyclic compound. There are common names for benzene derivatives, so when you have an OH, instead of calling it a hydroxybenzene or benzene-all, it would be called a phenol. When it's a methyl group, toluene, NH2, aniline, and OCH3, anisole. Here's when it's a double bond, this is styrene. When it's a ketone, acetophenone, aldehyde, benzaldehyde, acid, benzoic acid. Disubstituted benzenes have a nomenclature, so when their X and Y are 1,2 to one another, they're ortho. If they're 1,3, they're meta, and if 1,4, they're para. So here's ortho-dichlorobenzene, or 1,2 dichlorobenzene, meta chloroperoxybenzoic acid. Again, this is the parent benzoic acid, so it becomes meta peroxybenzoic acid. And then Phenol is the parent name, and this is paranitrophenol. When you have 3 or more substituents, you want to use as small as possible numbers, but the carbon with the functional group is listed as number 1. So in this case, these are all the same substituents, so you can start anywhere here. So it would be 1, 2, 3, 5, so it's 1, 3, 5, trinitrobenzene. And here, the parent is a phenol, so this would be 1, and so it would be 2, 4, dinitrophenol. Parent here would be the benzoic acid, so then it would be 3, 5, dihydroxybenzoic acid. Common names for disubstituted benzenes are shown here. This is metaxylene. This is mesitylene, O-orthotoluic acid, and this is paracresol. Phenyl and methylbenzene. So this would be a phenyl group, right? So it's when the benzene ring is directly attached. When you have a CH2 in addition to the benzene ring, that's called a benzyl group. And then if you look at names, this would be a benzyl bromide, this is a benzyl alcohol. So an important thing to note is that a benzene ring substituent is a phenyl group if it has 6 carbons. A benzyl group has an additional CH2 group, so this has 7 carbons in total. Physical properties of aromatic compounds, melting points. So more symmetrical than corresponding alkene, packs better into crystals, so they have higher melting points in terms of boiling points. They're dependent on dipole moments, so ortho has a higher boiling point than meta than para for disubstituted benzenes. Density, they're more dense than non-aromatics, less dense than water. And solubility, they're generally insoluble in water. They're very hydrophobic. UV spectrum, in terms of UV spectrum of benzene, there's 2 general peaks, one at 204, one 254. If you add another conjugation, that shifts to the right, going to 248 and 282. And here's a table, 16-2, showing the ultraviolet spectra of benzene and some of its derivatives, as I've shown you before in the picture. Benzene has a moderate band at 204 and a benzenoid band at 254. When you add ethyl groups, that shifts a little bit to the right, 4 nanometers in terms of the moderate band, 6 in terms of the benzenoid band. Metaxylene, again, that shifts even more. You have electron donating groups in there to the right. Bromobenzene, shifted to the right, and then styrene. Styrene is an added level of conjugation. As a result, you have a larger shift to the right. And so this ends Chapter 16, Part 2.